Hey there, so we're right in the middle of this massive energy revolution, right? We're swapping out old fossil fuel plants for huge fields of solar panels and wind turbines. And look, it's a shift we absolutely have to make for the planet. But it also creates this really fascinating engineering puzzle that we're going to unpack today.
Because here's the paradox. The very same tech that's making our grid cleaner is also getting rid of this invisible natural force that's kept it stable for more than 100 years. So that brings up a huge question. As we build this amazing green grid, are we accidentally making it, well, a lot more fragile?
To really get why, we need to take a step back and look at how the good old traditional grid actually works. And what's wild is that its stability wasn't really something engineers had to design from scratch. It was kind of an accidental, but very welcome side effect of the tech they were using.
At its heart, you can think of the power grid as this giant, continent-sized balancing act. The amount of electricity being made has to perfectly, and I mean perfectly, match the amount being used every single second. And that perfect balance shows up as the grid's frequency, that steady hum, usually at 50 or 60 hertz. If that frequency starts to wobble, you know the grid is in trouble. Now, the secret sauce to all that stability has always been this thing called physical inertia. You know, in those big old power plants, coal, gas, nuclear, you've got these massive super heavy turbines spinning away. The sheer kinetic energy locked up in all that spinning metal acts like a giant shock absorber for the whole system. It's not some fancy control system, it's just pure physics. And this, right here, is the fundamental difference we're dealing with. Those traditional generators are physically bolted to the grid, giving us all that inertia for free. But renewables like solar and wind, they don't have big spinning parts. They connect through really smart electronics, which means they have basically zero natural inertia. They just don't have that built-in physical cushion.
So that brings us right to the main event, the core challenge of this whole renewable revolution. As we shut down the old power plants, we are also, piece by piece, removing that massive, invisible flywheel that has always kept our grid humming along so smoothly.
And you can see it right here. We're moving away from a past that was dominated by these big synchronous generators, the SGs, to a future that's going to be run by inverter-based resources, or IBRs. With every single traditional plant that gets retired, the total amount of physical inertia on the grid goes down, and that makes the frequency way more jumpy and sensitive to any little problem.
The source material for this explainer had this fantastic analogy. Think of those big, powerful old generators as the trucks on the highway. They've got the engines, they provide the power, and they set the speed for everybody else. Solar and wind farms, they're the trailers being pulled along for the ride. They're designed to be grid following. They just add their power and follow whatever the trucks are doing.
So you can see where this is going, right? What happens when you start taking all the trucks off the road? What happens when your highway is mostly just trailers? Well, the whole system loses its muscle, its built-in stability. A single unexpected event, like a big power plant suddenly tripping offline, could cause a frequency crash so fast that all those grid-following resources just can't keep up.
But of course, engineers saw this problem coming a mile away, and they've been busy developing a whole new set of tools. And the first line of defense is this incredibly fast, really intelligent safety net.
It's called fast frequency response, or FFR for short. And you know, unlike inertia, which is just a law of physics, FFR is a deliberate, programmed action. Things like big battery storage systems can be set up to watch the grid's frequency constantly, and if it dips below a certain point, boom, they can blast a huge amount of power into the grid in literally a fraction of a second to stop that fall in its tracks. Okay, now this is a really crucial point. FFR and inertia are not the same thing. They do different jobs. Inertia is instantaneous. It's physics. And its job is to slow down the rate of the fall. It's the brakes. FFR is a tiny bit slower. It has to measure first. And its job is to stop the depth of the fall. It's the safety net that catches the frequency before it hits the floor. They're not interchangeable. They're teammates. So let's just walk through a scenario. A huge power plant suddenly trips offline. Instantly, there's a massive power imbalance, and the grid frequency starts to plummet. Whatever physical inertia is left on the grid tries to slow it down, but it's not enough. As soon as the frequency crosses a specific trigger point, all the FFR services kick in, injecting a wall of power to catch it and stop a potential blackout. It's like a perfectly choreographed digital rescue mission.
FFR is an incredible tool, but at the end of the day, it's still just reacting to a problem. The real long-term solution lies in changing the basic nature of our renewable resources, turning them from passive followers into active leaders. This means we have to actually re-engineer the power electronics, the inverters, so that they can provide these stability services themselves. Remember our trucks and trailers analogy? What if the trailers could not only drive themselves, but could actually become the new trucks leading the way?
And that leads us to incredible concepts like synthetic inertia. This is where you program an inverter to watch for a really fast change in frequency and then automatically pump in power to counteract it. It's programmed to behave just like a big spinning generator. You're basically digitally recreating that physical shock absorber that we've been losing. And this table just lays out the evolution perfectly. Most of the inverters out there today are grid following, or GFL. Those are our trailers. They need a strong, stable grid signal to follow. But the future is grid forming, or GFM. These are the self-driving trucks. They don't just follow the grid, they can actually form the grid's voltage and frequency themselves. They don't just rely on a strong grid, they actively create a strong grid.
So when you put this all together, what you realize is that we're not just trying to patch a problem, we are literally building an entirely new toolkit to engineer a smarter, more resilient grid from the ground up.
This new toolkit has it all. It has fast frequency response, that critical digital safety net. It has synthetic inertia, digitally rebuilding that physical buffer. And most importantly, it's got grid-forming inverters acting as the new leaders, the new backbone of stability. We even have other cool tools like synchronous condensators, which are basically just big spinning motors that provide inertia without making power to help us through this transition.
And this is really the main takeaway. These technologies aren't just a band-aid for a problem that renewables created. No, they are the fundamental building blocks, the key enablers that are going to make it possible to run a reliable, secure, and stable power system on 100% renewable energy.
Which leaves us with one last pretty mind-blowing question to think about. The stability of the old grid was, an accident of physics. It was inherent, but it was also dumb. The stability of the future grid will be completely engineered, controlled, and optimized by software. So could a 100% renewable grid built with these super smart, super fast tools actually end up being stronger and more resilient than the one it's replacing? Something to think about. Thanks for watching.